Hello students. So I'm going to ask you to download this file off of Jupyter Grades and to work on these questions before you listen into this review. Okay? Alright, so let's begin the review. Number one, the accompanying diagram shows some features of Earth's crust and upper mantle. Which model most accurately shows the movements of arrows associated with the surface features shown in the diagram? Alright, so we have, in the diagram, we have continents, we have the mid-ocean ridge, we have the oceanic crust, which is our basalt, we have granite, which is our continent, we have coastal mountains. Looks like there's some subduction going on here because I see the word trench. Alright, so anytime you have a ridge going to our reference table, all of our ridges, the Mid-Atlantic Ridge, as an example, arrows move apart. Going back to our flip lesson that we had on seafloor spreading, we have molten material, hot magma rises. Some of that breaks through the surface, creating the ridges on both sides and the rifting of those two plates. And any leftover magma is cool, becomes more dense, and it sinks, producing convection currents. So anytime you have a ridge, you automatically would have two convection currents there. All right, going back to the question. All right, let's look at these choices. So let's look at these arrows. All right, so the mid-ocean ridge, you have two arrows moving apart. Choice two arrows coming together. All right, that's a no-no at the ridge. Choice three, they're moving in the same direction, which should not be at the ridge. And choice four, you have arrows that come together, which should not be. So just by those arrows, I can eliminate choices 2, 3, and 4. Leaving you a choice 1. And just to make sure, we have hot molten material rising on both sides, and some of that makes it through the surface, creating a ridge. All right, so 1 is choice 1. Number 2, which combination of temperature and pressure is inferred to occur within the Earth's stiffer mantle? So we have choices 1 and 2 at 3,500 degrees Celsius, and choices 3 and 4 at 5,500 degrees Celsius. So let's try and eliminate some choices. So let's go to the reference table. Let's go to page number 10. So on page 10, let's go to our temperatures. We have 3,000 degrees Celsius and 4,000 degrees Celsius. And we know that 3,500 fits in between those two numbers. So if I bring that across, and once it hits my bold line here, I see that it's sitting somewhere between this dashed line and that dashed line, which would indicate that that is in the stiffer mantle, which is good. 5,500, right, sits in between these two numbers, and I bring that line across, and it hits my temperature curve there, and we can see that that temperature is the outer core. So we can eliminate 3 and 4 because that's too high of a temperature. Next, we have 0.4 millions of atmospheres and 2.0 millions of atmospheres. Okay, within the stiffer mantle, we have a range of pressures from, let's say, somewhere about maybe 0.2 up until like maybe 1.5 millions of atmospheres. So the number 2 would exceed that number of 1.5, and 0.4 fits very well between 0.2 and 1.5. So number 2, best answer would be choice number 1. All right, number 3, Base your answers to the following questions on the diagram below, which shows models of two types of earthquake waves. Alright, model A best represents the motion of earthquake waves called. So if you go back to the presentation that we had in class, so if you go to that slide where we have a slinky, and if you take your slinky and you go back and forth horizontally, right, that's going to send the energy horizontal, and eventually it's going to come back once it like ricochets off the wall. Next, for wave B, we have a vertical motion, right, up and down motion, and it sends like a wave, almost like an ocean wave, with a crest and a trough toward the wall, and it's going to go back the same way. Alright, so wave A are P waves, compressional. They're push-pull, horizontal motion. And then wave B, S waves, shear waves, transverse, vertical motion. So model A best represents the motion of earthquake waves called. Model A is horizontal motion, B is a vertical motion. So A really best represents P waves. Alright, as such, we can eliminate 3 and 4 because it begins with S waves. Next, we know that P waves travel faster than S waves. Alright, so we can eliminate choice 2 because it says P waves travel slower than S waves. So 2 is incorrect because of that fact. Alright, so 3, the best answer is choice 1. Moving on, let's go to number 4. Okay, number 4, on the map below, line AB is drawn across several of the Earth's tectonic plates in the South Atlantic Ocean. Which cross-section best represents the plate boundaries and mantle movement beneath line AB? Alright, so we have a Scotia plate, Sandwich plate, South American plate, and the Antarctic plate. Alright, so let's go back to page 5 for the plates, right? Plate tectonics. Rotate that so we can see that better. We're looking at this right here. Right, we have the Scotia plate, we have the Sandwich plate, South American plate. And there is convergence happening between those two ridges in the ocean. Okay, so we have to show two diverging. So we have A to B. We have one diverging here, another one diverging here, and they have to meet because that is a converging plate boundary. Alright. Going back to our legend, the side with the rectangles is the plate that stays on top, the overriding plate. The side with no rectangles is your subducting plate, which moves underneath the other plate. Alright, so based on this, the sandwich plate is the overriding plate, which means that it kind of stays toward the surface. The South American plate, right, is your subducting plate. It must move underneath it. Alright, so we can eliminate, if you're looking at your 4 choices, we can eliminate choice 4 because all these arrows go in the same direction. There's no diverging, no converging. We can eliminate 3 because 3 is showing 2 sets of converging, right? 2 sets of converging, eliminate 3. Okay, choice 2 is showing 1 converging and 1 diverging. Alright, and we know that we have to have 2 diverging. Choice 1 shows 1 diverging, the second diverging, and then converging in the middle, with our sandwich plate being the overriding plate and the South American plate being your subducting plate. All right. As such, for number 4, choice 1 is your best answer. Okay, going on number 5. Which block diagram best represents the relative direction of plate motion at the San Andreas Fault? All right, so San Andreas, a lot of you guys were discussing the movie in class. All right, so the San Andreas Fault is located on the west coast, right? That runs through California, through major cities like San Francisco and Los Angeles. And we have 2 arrows. One goes in one direction, one goes in the other, which is a type of transform plate boundary. Now for transform plate boundaries, there's no vertical motion there. I'm going to pull up a picture of transform fault boundary, like for California. Right, so this is all horizontal motion. One piece of the cross is sliding in one direction, and the other one is sliding in the other. Right? Horizontal. Keyword. Alright, going back to the question. Choice 1, they're not sliding past each other. One looks like it's diverging, and the other one looks like it's going in a different direction. Choice 2 is showing diverging. Choice 3 is showing converging. Choice 4 is showing 2 plates sliding past each other. Horizontal motion. Alright, so for number 5, the best answer is number 4. Alright, turn the page. Number 6. Which cross-sectional diagram of Earth correctly shows the path of seismic waves from an earthquake traveling through the Earth's interior? So we have earthquake epicenter at the top of each, all right? And we know that the P waves can travel through all types of media, can travel through solids, liquids, and gases. The S waves cannot travel through liquids. All right, and judging on page 10, and what we mentioned in class, if you notice the outer core, the temperature is above the melting point, which means it's inferred to be a liquid phase, right? The temperature is above that melting point, so it's going to melt, liquid. So the mantle is a solid, so we should have P waves and S waves traveling through the mantle on both sides. Okay, so choice 1 shows S waves traveling through the mantle, S waves only, which is not good. Choice 2 shows P waves only going through the mantle, which is not good. The mantle, right, the mantle is a solid. We have the asthenosphere, which is very viscous, very thick material. So S waves can travel through that, looking at the liquid phase, which is the outer core. So choice 3 shows P and S waves for the mantle. Choice 4 shows P and S waves for the mantle, which is good. Alright, so we can eliminate choices 1 and 2, left with 3 and 4. Now, if you look directly opposite of the earthquake epicenter, we have waves that go through the outer core, goes through the inner core, back through the outer core, and then toward the surface on the other side. And we know that the outer core is inferred to be a liquid, which means that the waves that go through the outer core has to only be the P wave. If we notice, choice 3 shows S waves going through the outer core, and choice 4 shows P waves going through the outer core. All right, based on that, we can eliminate choice 3 because S waves cannot go through the liquid zone, which is the outer core. All right, so 6, the best answer is choice 4. Okay, moving on, number 7. The diagram below shows the interaction of two tectonic plates. The type of plate boundary representing in the diagram most likely exists between the. Alright, so let's go back to our reference table. Let's go back to our plate tectonic map on page 5. Let's rotate the view so we can see it better. Okay. So we have two arrows that come together. There is subduction going on here, which means that there's a convergent plate boundary. And I see the word trench, which also helps me identify that it's a convergent plate boundary. Okay, so let's take a look and see. So you have the Antarctic plate and the African plate. Antarctic plates here, African plates here. We have a lot of divergent plate boundaries happening between those two, and we have some transform faults between those segments. Alright, so between the African and Antarctic plates, we have diverging plates, which doesn't answer the question. Choice 2, Antarctic plate and the Indian Australian plate. Indian Australian, Antarctic plates, and we can see we have arrows moving apart, which is diverging. So we can eliminate 2. Choice 3, South American plate and the Nazca plate. South American plates here, Nazca plates right here. We have arrows that come together, producing a convergent plate boundary, and take a look at that. We have the Peru-Chile trench. That works. Next, choice 4, South American plate and the African plate. African plate, South American. In between those two are the Mid-Atlantic Ridge, where these two continents are moving apart from each other. Alright, so we can eliminate choice 4. Alright, so the Nazca plate will be this oceanic crust. The South American plate here is the continental crust. And these would be the example of the Andes Mountains. Okay, number 8. The cross-section below shows a portion of the Earth's crust. Which observation provides the most dire evidence that crustoplate collision has occurred near this region? I'm sorry, most direct. I got cut off. Okay. So the most direct evidence will be located. Right, so all these layers have been folded like a piece of paper. Next unit, we're going to discuss that all these layers, sedimentary layers, all form horizontally first. And if they've been altered through plate collisions, they can be tilted, they can be folded, they can be faulted, all right, which can affect the ages of these rocks. All right, so which observation provides the most direct evidence that the crustoplate collision has occurred near this region? So we can see, first of all, these are all sedimentary rock layers. If you look at the map symbols, all right, if you look at your map symbols on page 7, looks like we have shale and limestone. All right, so first we have shale, limestone, shale, limestone. So I can tell you, choice 2, absence of igneous rock. Yeah, I mean, there's no igneous rock in there. we do have alternating layers of shale and limestone, but these layers, they're not horizontal anymore, right? They're folded like a piece of paper. All right, so your best answer for number 8 is choice 4. All right, let's move on. Number 9. Base your answers to the following questions on the earth science reference tables, the map, and seismograms below, and your knowledge of earth science. The map shows seismic stations in Chicago, Denver, Oklahoma City, and Tampa that recorded data from the earthquake. Seismograms A, B, C, and D show in Greenwich time the arrival times of the earthquake waves at 4 stations. All right, so we have seismogram A, B, C, and D. Looks like we have a few cities here. We have Denver, Oklahoma City, Chicago, and Tampa. Okay. So the question is, which seismogram was recorded in Tampa? If you notice, we have a time difference here between the P and the S. And they all have different durations or time differences. Now, Denver has the biggest circle. I would say Oklahoma City, right, going from biggest to smallest. Chicago, and then Tampa. Tampa has the smallest circle, which means that its time difference, right, if you go to page 11, the closer you are to the epicenter, right, the closer your time difference is. So your epicenter distance would be much smaller in comparison to a time difference very big. All right, so for instance, if it's a very small circle, you're going to have an epicenter of a smaller number. If your time difference is larger, then you're going to have a big epicenter distance. So Denver has the biggest circle, so Denver is going to have the biggest time difference. Tampa, smallest circle, smallest time difference. And what jumps out at me, being the smallest time difference, would be seismogram C. All right, looks like it's 234 and maybe 30 seconds or 40 seconds. And we have 236 in 0 seconds. All right, so 236 in 0 seconds minus 234, and we'll say 40 seconds for that. All right, so my time difference would really be about 1 minute and 20 seconds, which would be the smallest, just by observation. So number 9 is 3. Going on, number 10. What is the origin time of this earthquake? Okay, so number 10 is based on this diagram. So if we know that seismogram C is Tampa, and the P wave came in at 234 and let's say 40 seconds, the time of origin has to be before 234 and 40 seconds. Okay. Right? The earthquake had to have occurred before the P wave gets to these stations. So if seismogram C is Tampa and it's at 234 and 40 seconds, it has to be before that. Now I can eliminate choice 4. 237 comes after 234 and 40. I can eliminate 3, right, because 235 and 40 comes after 234, 40. I can eliminate 2 because it's exactly at 234 and 40. There is some time for it to get there, which means it has to be before 234 and 40. Next is 233 in 0 seconds. Now, once you print this out, right, you're going to take your distance, right, go from the epicenter to the line, and you should measure about 700 kilometers. Now, if I go back to the reference table, and I have 200, 400, 600, and 700, and I bring this directly up, right, it's about maybe a minute and 50 seconds as my travel time. Okay, so if I take my 234 and 40, and I subtract that from 1 minute and 50 seconds, do my time math, my 34s cancel out to a 33. I add 60 to my 40, which comes out to 100 seconds. So 100 minus 50 is 50. 33 minus 1 is 32. And I have 2 hours there. So doing my travel time, I would have a time of origin of about 2 hours, 32 minutes, and 50 seconds, which is super close to choice 1 anyway. All right, so the best answer here for number 10 is choice number 1. All right, number 11. The P wave generated by this earthquake took 2 minutes and 40 seconds to reach one of the seismic stations. Approximately how long did the S wave take to reach the same seismic station? Okay. Okay, so it took the P wave 2 minutes and 40 seconds. How long did it take the S wave to reach the same station? So here's what we do. So we have a travel time of 2 minutes and 40 seconds. So here's my 2 minutes, 2 minutes and 20, 2 minutes and 40. And that's the P wave. So I'm going to take this line, bring it across until it hits the P wave, which happens about here. My epicenter distance is 1,200. So how long, what's my travel time for the S wave at that same station, the same distance of 1,200? I take that same location, I bring it up until I hit the S wave. Hits about here, and I bring this across, and it occurs sometime between 4 minutes and 40 seconds and 5 minutes and 0 seconds. All right, so based on that, we can eliminate 1, we can eliminate 2, we can eliminate 3. And of course, between 4 minutes and 40 seconds and 5 minutes, we have 4 minutes and 50 seconds as the answer. All right, so 11 is 4. All right, moving on to number 12. Base your answer to the following question on the diagram below, which represents seismic stations A, B, and C. The distance from each station to an earthquake's epicenter is plotted. The epicenter is closest to point. All right, now we have station A, B, and C. And if you remember correctly, right, we need, in order to triangulate, we need 3 stations, right, 3 circles. And where all 3 circles intersect is where we have the epicenter. So here we have 1 circle with an infinite number of locations. We have a second circle, which would intersect at 2 locations, right here and there. And your third station, let's say Houston, would pinpoint that exact location. So bringing the other lesson that we had, the introduction to triangulation. All right. So if we have 1 station, we have an infinite number of locations, right? We can have 1, 2, 3, 4, 5, 6, 7, and you can make as many X's as you can. If we have 2 stations, it's going to intersect at 2 spots now, right? 1 and 2. Your third station is going to pinpoint that location. So my third station now will pinpoint my epicenter over that point, where all 3 circles intersect. If I put this on a Google Earth, we have 1 station of Miami, which is red. We have Lima, Peru, which is yellow. and Dakar. It looks like off the coast of Africa, and that's in blue. And all three circles intersect, and that's that white point called the epicenter. So station F only has two places where it intersects. All right, so F we can eliminate. E, only two circles intersecting, we can eliminate E. We have G, only two circles, station B and C, intersecting. Station D, location D is where all three circles from each of these stations all intersect. So the epicenter would be at location D. All right, once again, locations E, F, and G, that's where only two circles intersect. All right, and your third station will pinpoint that. All right, ladies and gents, that concludes the review. So please make sure you study. Any questions or concerns, you can see me for extra help on Mondays and Tuesdays, period 7. All right, have a good night, and thank you.